let's continue. I'd like to get into next the sample standard deviation. And before we get to that, because it has to do with the sample standard deviation, discuss bias in sampling. When I say bias, or we say in statistics biased in sampling, we don't mean like prejudiced in sampling. That's a totally different thing. What we are looking for when we're a sample is truly a random sample of the population. That is often the most difficult thing to get. And it's kind of my opinion because I see what people do, and it really isn't a good indication or good actual random sample of the population. All of this mathematics, all the proofs that go along with this are assuming that that sample is unbiased, meaning it's random, truly random, and then you can mathematically prove the results. But if they're not, it's an if-then statement. If it is not truly random, then the results aren't necessarily true. So, so that's part of the issue we want to discuss. Now, when it comes to the sample standard deviation, it's more concrete of why why this formula I'm about to show you has to be true. So, bias in sampling could be, if you're looking at the population for, say, students that are, or not students, but people between a certain age. If you're only sampling college students, that would be a biased sample because not every type of student is in college, or a person of that age is in college, even if you account for age, right? So another one, there's a bunch of them you could just look up, but I wrote a couple down. If you are doing a sample and you're only sampling people who watch certain news channels, certain news organizations, whether it's this one or this one, we all know there's a huge difference in what people watch. It's not how it was when I grew up, but that's what you have to be careful of what you hear. And so the sample, if you're just looking at them, that is going to be a different result than a truly random sample of your population. But it doesn't have to do with people. So this is the other thing I wanted to make sure of, is that a lot of this statistics has to not do with people. This has to do with things. So if you sample, you're brewing beer and you always sample the first batch of beer. Well, that's a biased sample. If you want the population to be all the batches of beer you make, you got to randomly sample those. So first run of building bolts or something, you don't check just the first run. You check the first run, the 5th run, the 12th run, whatever. So you have to consider those sort of things when you're doing your sampling. Okay, so that's what can happen, and that's what's called bias in sampling. So the next concept is the sample standard deviation, and that looks like this. So we're going to let n, we'll use little n. Sometimes, and I'm not sure this is totally true, but sometimes capital N represents the population and little n represents the sample, but not necessarily. But in this case, that's what I'm going to do. So let n be the sample size. That's the key idea there. The sample size and the x sub 1 to x sub n be the n observations. In the sample. And so now we can't use mu. We don't know mu. We use x bar. So, and x bar, the sample mean. So it's the mean of the sample. We don't know what mu is. So we know x bar of that sample. You add up all the x's, x values, divide by n, etc. Okay, then the sample standard deviation, S, is slightly different. It's the square root of this sum. So it's the square root of the sum of the squares, x sub I minus x bar. So you do the same, that's the same calculation, except you're using x bar, not mu. But then you end up dividing, so normally for population, right there, you divide by n. So for us, we don't divide by n, we divide by n minus 1. So you take, so the value is going to be a little bigger than if you knew the entire population. So S squared is the sample variance. And S, if you take its square root, is the sample, excuse me, standard deviation. So why do you divide by n minus 1? And there's, mathematically speaking, statistically speaking, it really is mathematically, when you derive all this stuff, there's a good reason for that. The explanation for that is that the standard deviation is looking at the variability of the population, right? You're trying to look at the variability of the data points. And so when you do a sample of all the data points, so this is the best way I found to explain it. If you sample, so you have all the data points, you have the population, but now you're sampling them. That is inherently going to be a larger variation, not that variance, larger variation than the actual population. So this accounts for that variation of the mean, of the sample mean, in its inherent of what you're doing. So you have all these data points and you're sampling. There's going to be bigger variability there, all right? So that's the idea. It has to do with the concept of degrees of freedom, which if you looked it up, you'll inevitably run across that. Degrees of freedom. So you say in this case there's n minus 1 degrees of freedom, and you could talk about if you're selecting things from a box that selection has n minus 1 degrees of freedom because like the first selection isn't a degree of freedom. You could talk about stuff like that, but what I like to think of it is you're dividing by a smaller number. So this number is a little big. So the variability that you're reporting for the sample is bigger. Well, that makes sense because when you sample things, you're inherently going to get a bigger variability in that sample. So I like that concept of it. Frankly, you don't even have to worry about it. Just make sure if you got to read, is it sample or population? And then you do that. And in Excel, you literally have to put in sample or population, and it does that automatically. And we can all look up what the formula is, and we'll go over that when we get there. Another way of saying it, I wanted to write this down too. Degrees of freedom is n minus 1 and not n. There is less bias in the sample, in the statistic. So by dividing by n minus 1, you have less of a bias estimator. So less bias in the statistic or estimator. So that's the concept. So you just got to divide by n minus 1. Okay, so here's an example. Sometimes I won't do all these. I did the first one. So let's suppose you have, so let's let A equal this set, 1, 1, 1, 2, 5, 5, 5, 9, 12. And we'll have B equal this set, 3, 4, 5, 5, 5, 5, 6, 7. And then we'll do these two things. So find X bar for both and 2S for both. All right, so you go ahead and try that and go ahead and pause now. And then I'll go and do the calculations. So for both, you get 5, which seems kind of reasonable, right? Because all those 5s in there. But it's actually 5 for both. And when you calculate S, the sample standard deviation for SA, it's 3.89. And then for B, this is what you would expect just by looking at the data. Everything's closer together, 1.2. So there's a good visual, well, it's not visual, but it's a good way to look at it. When you look at those, it's up there. When you look at those, you can see 1 to 12 is a pretty big difference. This one only goes up to 3, only goes down or to 3 and 7. So the difference between all the means aren't as much. So you can kind of see that it's not as spread out. That's the key. It's not as spread out. But it's more than that. It has to do with the concept of empirical rules and how much data, how much of the information is within those standard deviations. So that's the next concept. This is called the empirical rule. This is kind of a prelude, warm-up to the next thing we'll be looking at. There's an empirical rule. Says this. I'll make it real brief. So if you have, these are intervals. So these are intervals in the concept. So this can be sample, but this is actually population. So empirical rule says mu minus sigma to mu plus sigma contains, I'm going to have to move that, contains approximately 68% of data points. Of values, data values. So, and then if you do multiple standard deviations, so mu minus 2 sigma and mu plus 2 sigma contains 95% of all the data points. So you could think of like heights of people. So if you're 2 standard deviations from the mean, then there's only 5% of the population that's your height, or right? And then if you go higher, then it's even more. So then mu minus 3 sigma and mu plus 3 sigma, that contains approximately 99.7% of all the data points. So if you're 3 standard deviations, whatever this standard deviation is, from the mean, then you can argue this is not a guess. This is statistically has to be true, because remember, you calculated sigma by using all the data points. So what this has to do with is the bell curve concept and how they taper off. So like that's 1 standard deviation, that's 2 standard deviations, and 3 like way out here in the tails. So you barely have any out there. Okay, we'll talk more about that later, but that's what the empirical rule is stating. Okay. All right, so there are a few examples like that to look at, and look at some of the homework, and I'll see you in the next one.